All right, so I figured I'd just do a quick review to help you. I kind of talked about this stuff in class, but now you have a little place to come and look at it. Okay, so let's jump right in. First of all, I'm just going to kind of look back through the problem sets a little bit. Um, when it comes to related rates, remember the biggest thing is setting up a relationship and then taking the derivative. So for example, if I'm looking at something like number 4, if I want to find the rate at which the radius is changing, the first thing I would do is write down what I'm trying to find. Like I'm trying to find the rate at which the radius is changing. Then I need to make a relationship. Well, if gas is being pumped in, that's a volume and it's a rate of volume. So boom, I immediately know I need volume. For a sphere, it's 4/3 pi r squared cubed, excuse me. And then the next thing I'm going to do is take the derivative so I can introduce the dv dt. Take the derivative, bring the 3 out front, I get 4 pi r squared. Don't forget to attach the dr dt. And then you're just plugging in what you know. The only thing you won't know is the dr dt, and so then you can solve for that. I think we're pretty good on these Pythagorean ones. For the conical cups and cylindrical tanks, things like that, for the cone ones, the biggest thing with a cone, don't forget with a cone is that the ratio of the radius to the height stays constant. So even though the formula for volume of a cone is 1/3 pi r squared h, you don't want to have both those variables. So what we typically will do, it all depends on what you're trying to find. Like in this case, I want the rate of change of the height. So I want to leave the dr dt in, I want to leave the dh dt in the problem. So I would over here say, okay, like my radius to my height is, let's see, they say the radius is 3 and the height is 6. That's 1/2. So then I can cross multiply and I can solve for the radius. Then I'm going to plug that back in. So then I have 1/3 pi, instead of the radius, I have h over 2 squared times h, which is going to give me, let's see, h squared times h is h cubed. If I square the bottom here, I get a 4 times the 3 that's already on the bottom is a 12. And now I have my volume. Now I can do the derivative of both sides. So now I've got a dv dt. I'm going to take the 3 out front and reduce it with the 12. I get pi h squared over 4 dh dt. And then, as you can see, I'm ready to start plugging things in to solve backwards. Okay, ones on the back you can continue. They're pretty much the same. Again, here we have like in 17, oil is spilling. The area increases at a rate of this. That means you know dA dt. As soon as you know what you want to be dealing with, it really shouldn't be too hard. So I'm going to set up area. Well, it's a circle, so pi r squared. I'm going to take the derivative of both sides. That gives me like a dA dt, and I get 2 pi r. Don't forget your dr dt, and then I can go from there. I think that you guys can pretty much handle that section. I mean, you need to review them, but you can handle it. For linear approximation, the biggest thing for these, this is writing a tan line to approximate. If you want to approximate, remember, you need the slope and you need a point. And the way that you get those vary. If you're doing problems like this, and I want the equation of the line, and they usually tell you where they want you to approximate it, then to get the slope, you're going to use the derivative. So I'd find the derivative first, which for this was easy. I mean, they're going to be trickier. And then you plug in 1, and there, boom, there's your slope. And then your point would be whatever you get when you plug in 1 to the original equation. So when I plug in 1 to the original, I also get 1. So I'm using the slope and I'm using this point, and then I'm writing the equation of my line. Now you can write it with the old school version, or you can move the y over to the other side and you can have it like this. Then when you're ready to approximate, you're literally just plugging in. So in class, I talked about how on this last question, I ask you to do the same thing at x equals 2. So we need the slope at 2. Well, we don't have the equation, but we have the information because we have the derivative or the slope at 2. So we know we're going to use 4. If we need the point, we also don't have the equation, but that's why they give you this. So you know that at 2, I get 1. So then once again, you can create your equation to help you approximate. Again, if you want to, you can bring that 1 over. So then when I plug in something like 1.9, I can do this without a calculator. This is negative 0.1 times 4, which is negative 0.4 plus 1, or 0.6. Like you can handle that. Okay, so linear approximation should be pretty easy. Extrema, again, the biggest thing with extrema is making sure that you're actually plugging in the endpoints if I'm looking for the absolute extrema, and being careful with that. Remember that critical numbers are both zeros at the top and the bottom if you have a fraction. For mean value theorem, I would just say make sure for mean value theorem, first of all, it has to be continuous and differentiable. So you need to make sure that that's a truth statement. And it only has to be continuous and differentiable on uh, the interval that you're looking at. So, like, for example, here on 6, this function is discontinuous at 0, but it's not part of my interval, so I don't have to worry about it. So then if you want to do MVT, remember you're plugging in the values of the x's that you're looking at. So if I plug in 1, for example, I think I get a 5. If I plug in 4, I happen to get a 5. Then you find the slope between these two guys, which is 0, just happens to be 0. Could be anything other than 0, but it worked out. And so then what I know is that somewhere between 1 and 4, my slope has to be 0. How do I find that value? That's when you have to start taking the derivative and setting it equal to whatever the slope is. Again, in this case, the slope happened to be 0. Had this been 1/2, I'd be setting the derivative equal to 1/2. For the first derivative test, remember, again, first derivative test tests for increasing, decreasing intervals. We always include our zeros. So we're talking about using brackets unless you can't plug the original value back in. So if, for example, you got one of your zeros to be like 1. If I try to plug 1 back into this, I get 1 minus 4, which would be the square root of something negative. I can't do that. So then I wouldn't want to include that. So that does help. So you can always look for things you can get rid of. I will also say when finding the derivative with e's, you guys got to be able to find the derivatives involving e. So like in this case, this is a product rule. So the derivative of the first is 1 times the second plus this first times the derivative. The derivative of e is e to the whatever times the derivative of what's inside. So that just going to make that a negative. Also, remember, eventually you're going to be setting this equal to 0 here because you're looking for maxes and mins. You're almost always factoring that e out. So in this case, I would end up with a 1 minus x. Remember that this part is never 0, so you don't have to worry about an e becoming a 0. So the only time this was 0 was actually at 1. And then I can plot 1 and I can test both sides. Remember, you're plugging it back into the derivative. You want to know if it's increasing or decreasing. And then you only have maxes and mins again when it switches from being increasing to decreasing or vice versa. Okay, so moving on to second derivative, remember that second derivative tests for concavity. If it's positive, it's concave up. If it's negative, it's concave down. You can also plug in the derivative values that are 0 to test for maxes or mins. If you plug in a 0 of the first derivative and you get concave up, then that would mean that has to be a min, whereas if it's concave down, it's a max. I think you guys have a pretty good handle on this. It's just the algebra and making sure you can do your derivatives correctly. Okay, on to the graphs for the first derivative. So this is where some of you have had some issues and you're getting better, but you need a little work. So if you already have the derivative graph, remember it's nice if you can think of what you're looking for over here on the left and then relate that to the graph. So if I want to know where f, the original, is decreasing, remember f is decreasing when the derivative is negative. So you're looking for when this graph is negative, which would be from -1 to 2. If I want to know where it's increasing, remember, the original is increasing when the derivative is positive. So I would be looking for when my graph is above this axis, because this up here is when it's positive, this is when it's negative. Okay. If I want to find any minimums on the original, remember, maxes and mins are when the derivative is 0, and then you have to kind of see how it's happening. So like these are potential maxes and mins. Because this goes from being positive to negative, you know that was a max. So there's a max at -1, and because this goes from negative to positive, you know that's a min at 2. Concavity is when your derivative is increasing. So you're looking for increasing/decreasing intervals. So concave up is when it's increasing. So like I would go from here over. So from 0.5 to infinity. It's concave down or decreasing from negative infinity to 0.5. And then points of inflection, remember, are maxes or mins of the first derivative. So there's one point of inflection at x equals 0.5. Okay, so in this one, here we go again. We have the graph of the derivative, so that is important. You always want to make sure that you know what you're talking about. We want increasing and decreasing. So again, I'm decreasing when it's negative, so from 3 to 5. I'm increasing here. Now, this is interesting because I'm positive here, and I remember if I don't actually switch, that's still considered increasing. So from -2 all the way to 3. Maxes and mins. Maxes and mins, remember, are when the derivative is 0. So since I have the derivative graph, I'm looking at these guys. But unless it switches, it's not a max or min. So the only one that actually switches is right here, and that goes from being positive to negative, which means it's a max. So the only max is at 3. Concavity, when you have the derivative, is when we're increasing or decreasing. So concave up would be when you're increasing. So that would be from like -2 to 1, 1 to 2, and 4 to 5. Concavity would not be inclusive though. So -2 to -1, 1 to 2, and 4 to 5. If you wanted to do concave down, that would be when it's decreasing. So those two sections. And then points of inflection would again be maxes or mins of the derivative. So I've got 1, 2, 3, 4. So at -1, 1, 2, and 4. I think you get that. There are some good ones back here too that deal with just the way that the graphs interact. You guys have seen this before where I look at the values. Now remember on these guys, f of 1 is the actual value, which is 0. The derivative means the slope at 1, so the slope is a positive number. And then this is concavity, which you can tell it's concave down. So that's how I'm able to order it from largest to smallest. With optimization, again, you guys let yourselves get so nervous about this. You can do it. Set up the relationship you know, try to get it down to one variable and solve. A lot of you have trouble with some of these, so let's look at these real quick. Like this one, you're selling shoes for $50 and you're selling them for $50 when you have 100 pairs. So that's your first relationship. We know that each pair is going to get sold for $50, but that's going to change. As you go up by a pair, you reduce the price by 20 cents per pair. So there's my change. As this goes up, this guy goes down. This is how much I'm bringing in, so my total. And then if I want to find, this is nice because you only have one variable. So then if I want to find the max, I'm going to have to take the derivative and then set it equal to 0. This I would expand by hand and then take the derivative and set it equal to 0. For this, the window one down here, that did get some of you guys. It was a calculator problem. I honestly think that you can handle it. If you want to, I know I've gone over it in class. You can check back and look in your notes. For velocity and acceleration, my big thing is this. Just remember that having a positive velocity means that you're going if it's greater than 0, that means that you're going to the right, and having a negative velocity would mean that you're going to the left. So if you want to know when it changes direction, you're looking for when the derivative is 0 and actually does make that change. Like if you had a graph, you would need to make sure if this was the derivative graph or the velocity graph, you would have to make sure that it does actually go through the x-axis. So it would change directions here and here. Again, speeding up and slowing down just refers to if you have the derivative graph, if it's headed back towards the x-axis, it's slowing down. If it's headed away, it's speeding up. Or you can plug in both the value for the acceleration and the derivative, the velocity, and see if they're the same or opposite. All right, I hope this has been helpful. I'll see you in class tomorrow.